Okay. Hello, everyone. Um, so in today's meeting, we're gonna discuss about differential calculus. So everyone is already familiar with single variable calculus, so I won't bore too much with that. Um, but I want to generalize the derivative not just to Rn, which might seem natural, but to a broader class of vector spaces. Now I know that there are generalizations to locally convex spaces and whatnot, but I think I think for vector spaces and topological vector spaces, I think that what we have, like the generalization that I want to do is sufficient for what we want to talk about and any sort of derivative you might see in this field. Um, at least in practice. Again, I'm not too familiar with anything outside of this. So if there is, I mean, I would love to know about that. But yeah, so we're gonna try to generalize to all inner product spaces, but um I mean there's an obvious there's an obvious there's an obvious blockage that we have. And that blockage actually shows up in single variable calculus. And we're gonna let's explore this. So the first central question I have is why even define calculus on the real numbers? Right? Why define calculus on the reals and not Q, for example? So why the reals and not Q? Okay. So let's see this. So we know that Q inherits the subspace topology from R, and so it's a topological space in its own right. We also know, so because it's a topological space, we can talk about continuity. So so we're going to consider the following function. Okay, kind of consider f from Q into Q, and it's going to be defined by the following. So it's going to be f of x is going to be 1 and 0, and it's going to take only two values. So it's a very simple function. So it's x, so when x squared is less than 2, it's going to be 1. And when x squared is bigger than 2, it's going to be 0. So okay, let's graph this function. So I'm going to graph it again, pretending that we're over the reals. I mean, and because Q is dense, it doesn't really matter too much. So I'm not gonna bother drawing like dots, even though technically there are dots because Q is not connected. Um, but yeah, so it's okay. We have so everything on this side, so here and here, we have x squared is bigger than 2. So what we're gonna do is we're gonna just color that in with yellow, let's say. So it's okay. It's 0 here. And then it's 1 in this region. Okay. So first thing I want to note is that this function is not continuous in Q. So this is not continuous over Q. Okay. It's not continuous over Q. And the reason for that is if I get like arbitrarily close. Sorry, I misspoke. This function is continuous over the rationals. Okay. Um, this function is continuous over the rationals, but it's sort of troubling because the graph is clearly discontinuous, right? Um, Now again, one might argue that because we're looking only at functions from Q to Q, um, this is actually a continuous function, and so it shouldn't really matter too much. Um, but another thing we want to notice is that this function is also differentiable. Okay, differentiable over Q in the usual single variable calculus sense. But the issue is, the reason I say that this is a troubling example is because good theorems like the intermediate value theorem don't hold. But now, okay, the intermediate value theorem doesn't even hold because Q is not connected. So connected spaces are, sorry, disconnected spaces are sort of troubling, but at the same time, like if your space is not complete, then you have these holes, and then the intermediate value theorem may not hold anymore. So, okay, we're going to restrict ourselves to complete spaces. Okay, this gives motivation to restrict to complete spaces. And moreover, we're going to also, because because as we'll see, we'll use the definition of the norm. So we could restrict ourselves to Hilbert spaces, but inner products also induce norms. So what we'll do is we'll restrict ourselves to Banach spaces. Sorry, I guess Banach spaces are normed spaces. So my bad. So we could restrict ourselves to Hilbert spaces if we looked at only inner product spaces, but we're gonna broaden this definition slightly, and then consider Banach spaces. So we're gonna restrict ourselves to complete spaces with a vector space structure and a norm. But these are simply just Banach spaces. Okay. Um, okay. Okay. So let's see. Now, how do we define the derivative? What is the derivative? So there are many good equivalent definitions for the derivative over the real numbers, such as you want to be able to give the best linear approximation to your curve, for example. And that's one way to look at the derivative, is the best linear approximation, but it's hard to really if we just look at the original definition of the derivative, it's hard to make the leap of faith into that definition and why we would restrict ourselves to that definition. So one thing we could do is we can consider the derivative of um, single variable functions, but that take values in a Banach space. So suppose we have gamma, and it's defined on some interval into some Banach space. X is a Banach space. And every time I talk about Banach spaces, it's going to be real Banach space unless I mention otherwise. So okay, suppose X is suppose X is a Banach space, and now we can just define the derivative at zero of this curve to simply be the limit as t goes to zero of gamma of t minus gamma of 0 all divided by t. Since t is a number, everything here makes sense. And since we have a metric, the limit makes sense and so on. So, so okay, we've defined the derivative for a curve. And now this is a very nice definition. It is exactly the definition we would expect um, from the single variable case. But but it's not exactly what we want, right? I mean, sure, we want to be able to differentiate curves, but there's many other functions that we would like to differentiate. So how do we generalize this? And before we even generalize, let's specialize the case when x is equal to Rn. What happens when x equal to Rn? We know that gamma of t can be written as gamma I and then ei, where ei is the standard basis for Rn. Um, and then since Rn is the product of R n times, the product topology forces us that the limit exists in the product topology if the limit exists in each of the individual components. So we can see that gamma prime of 0 is simply going to be gamma I prime at 0 times ei. Okay, that's nice. Now let's see how we can generalize this definition to functions between Banach spaces. So so how to generalize to functions between arbitrary Banach spaces. And there's one pretty obvious way. So we can just take a curve in our space and we can ask how much does my function change along this curve, right? But why can we do this? Well, the simple answer is Banach spaces are path connected. So no, X is path connected. And we can see that it's path connected very simply by saying A is connected. So and are connected by A plus TH. So um sorry, but they're connected by 1 minus T times A plus T times H. Okay. So basically at T equals 0, we start at A, and then um, as T goes to 1, um, the point A moves to H. So, okay. Um, this tells us that it's path connected. And again, this exists because it's a vector space. So what we can do is we can take this curve um, and we can work with this curve. So now let f be, I'll call this curve gamma of t. So let x be a function from x to y, and x and y are Banach spaces. Then, then what I can note, actually, I'll not call this gamma for now. Then I can move a in the direction of h, right? So if I consider gamma of t equals a plus t times h, this fixes a, and then we move we move parallel um, to the vector associated to h that comes off from the origin. Um, then note that if we consider gamma composed with f, right, this is a curve from whatever interval gamma is defined on into y. But since this is a curve, we can differentiate this. So we differentiate this. We can differentiate this and sheet this to get f prime at 0. And we're going to call this the Gâteaux variation. So this is called the Gâteaux variation of f along h, along the direction of h or along h. So, okay, this is one notion of differentiable we have. Um, Now, one might ask, is this notion sufficient? Is this notion good enough for whatever application we might need? And as we'll see, the answer to this is no. Um, but just to get some terminology out of the way, we say f from x to y is Gâteaux differentiable at a in x if there is a map there is a map that I'll call delta f of A from x to y such that um, delta f of A at h is the Gâteaux variation of f at A along h. So we require, so firstly we require this to exist for all h and x. Okay. And moreover, we require there to be a function um, that maps it this way. We don't require this function to be linear or anything. Um, and as we'll see, this sort of um, not having it linear is sort of an issue, um, as we'll see in just after this example. So, um, okay, and we call delta f at a, we call this the Gâteaux derivative of f at a. Okay. Now, let's see an example of where the Gâteaux derivative is not a sufficient notion of differentiability. And this example will sort of show us that being Gâteaux differentiable does not even imply that our function is continuous. Okay, so the Gâteaux derivative is not strong enough. So it's a pretty weak condition. A lot of functions are Gâteaux differentiable that we wouldn't expect to be differentiable. Um, so we can consider the function f of x from f from R2 into R given by f of xy equals x squared y over x to the 4 plus y squared if x, y are not 0. But if they are 0, we just assign 0. So first we'll show that this function is Gâteaux differentiable. So let h equal ab. Then the Gâteaux variation of f at 0 along h is given by the limit as t goes to 0 of f of 0 plus t h minus f of 0 divided by t. Okay. But f of 0 is 0, so that's fine. And f of th, if we write this out, is simply 1 over t times t squared a squared times tb divided by t to the 4 a4 plus t square b squared. Okay. And now let's simply factor out a t squared from the denominator. So we're left with t squared a to the 4 plus b squared. And now this t cubed cancels out this t cubed, and then if we evaluate this at 0, we get a squared divided by b. Okay. So the first thing to notice is that this um, is not linear in H. Okay. This contradicts our idea of what we think the derivative is, um, because the derivative of a function from R to R is a number, and we can always treat a number as well, the derivative at a point is a number, and we can treat that derivative as multiplication by a scalar. So derivatives at a point are linear, but the Gâteaux derivative may not be. Moreover, the Gâteaux derivative is not even continuous. At, so it exists at 0, and in the 0 direction, it's trivially 0. Because here you would have f of 0 minus f of 0. Um, so it's so the limit exists at 0. Sorry, not the limit. The value exists at 0. It's 0, but we'll show that it's not even considered. Sorry, it's not even continuous. To see this, consider um, so consider the limit as ab go to 0 of a squared over b squared. Now, if we if we hope for this to be continuous in AB, um, we'd we'd have that this is the limit when it goes to zero is one. Sorry, is zero. But if b equals a squared, so we move along the parabola b equals a squared, then we note that this limit is just a squared over a squared, which is 1, which is not equal to 0. So it's not even continuous. Okay. So f is not continuous. F is Gâteaux differentiable. Um, the action of the function of the Gâteaux derivative is not continuous in the direction. So there's so many issues that happen with the Gâteaux derivative. So the Gâteaux derivative is extremely weak. I didn't prove that the function is not continuous. So let's do this now. So note f is not continuous. And to do this, what we're going to do is we're going to take the limit as x, y go to 0 of x squared y over x to the 4 plus y squared along the same parabola. So we're going to go xy equals t squared. What this gives is that the limit as t goes to 0 of, so x squared, so we get t squared times t squared, so we get t to the 4th in the numerator, divided by t to the 4 plus t to the 4, so that's 2t to the 4, which is 1/2, which is not 0. So the function is not even continuous. Okay, so this is quite troublesome. I mean, the function is not continuous. The Gâteaux derivative exists. The action of the Gâteaux derivative in the direction is not linear. It doesn't is not even continuous, right? So there has to be a better definition. Again, the Gâteaux derivative sees applications in some places. So in some sense, it is useful. But we will always restrict ourselves to this so-called smooth situation, at least for most of this, for most of what we're doing. Um, and for that, we'll see that the Gâteaux derivative and the derivative we'll define now, um, they agree on the values. So, so okay, we have to sort of revamp this definition of the derivative, right? So let's go back to the single variable case and see if that holds for Banach spaces. Right? So if f is a function from R to R, then f prime of A is defined to be the limit as h goes to 0 of um of this. Okay. But now we saw that if we treated h as a parameter in R, um, this limit sort of is wonky. So the only other option is h is in the Banach space. But if h is in the Banach space, then this limit is, this doesn't even make sense because firstly, we're dividing by a vector. What does that even mean? So, okay, this is a little problematic. One way to go around this is to note that the norm function is continuous. And since it's continuous, we can just take norms of both sides and say, okay, the derivative is this vector such that the norms, so if I can put norms like this. Um, But that's also problematic. And the reason for that is we have a whole circle, or sorry, a hypersphere's worth of points that your function could go to. So this may not be unique. And how do you pick one? Right? That's another issue. So what we're going to do is we're going to rearrange this definition a little bit. So we're going to move things around. Um, and we're gonna treat the derivative as a linear approximation. And now we can take norms. And the reason we can take norms here is because only one vector has norm 0, and that's the 0 vector. So if we can find such a vector, um, if we can find a vector, sorry, not a vector, if we can find a map f prime, So that this limit in norm goes to zero, then we're done, right? We have a derivative. So let me let's write this out. A plus h minus f of a minus f prime of a times h divided by the norm of h. Okay, now we can directly generalize this. So if f is from x to y, and these are Banach real Banach spaces, uh, we say f is Frechét differentiable at a in x if there is a linear map that I'll call df at a from x to y such that the limit as h goes to zero. So now h here is a vector in the Banach space. Um, and then the norm of a plus h minus f of a minus df at a of h over the norm of h is zero. And now we have to be a little careful. So here the norm is in y, and here the norm is in x. Okay. So in other words, we see that df at a is the best linear approximation in the sense that the remainder goes to zero very quickly compared to h. So the error is at most h squared, and when I say h squared, I mean the norm of h, then squared. Um, yeah, okay. So now the Frechét derivative is very good. Frechét differentiability implies continuity. Okay. Um, and that's because we sort of see that the norm has to get close. So we see from the get-go that this function over here is not Frechét differentiable because firstly, um, if I if I take the curve like along one line, the limit doesn't agree linearly, so it's not even Frechét differentiable. Um, but now what we can note that if f is Frechét differentiable, then f at a, let me mention that, Frechét differentiable at a in x, then f is Gâteaux differentiable at a. And to see this, it's very simple. I mean, we can, like I said, we can restrict h to move along a path, along a curve that goes to A, and then we see that it's precisely what we want. Okay, so Frechét differentiable implies Gâteaux differentiable. We've seen that Gâteaux differentiable, note also that Gâteaux differentiable may not imply Frechét differentiable. Okay, so in some sense, the Gâteaux derivative is weaker. And so more functions are Gâteaux differentiable. But what we can do is if um, the Gâteaux derivative is linear and continuous in A, um, I'll talk about what that means in just a little bit. So if it's continuous in A, then F is Frechét differentiable. Okay. So we see that. Okay, so let's talk about what it means for the Gâteaux derivative to be continuous in A. Um, it also has to. It also has to be continuous in H. So if it's just a continuous, so let's let me reword all of this actually. So if so now it takes in two things and it gives you one. Um, if this is a continuous map, and if I restrict onto each fiber, um, if I restrict onto each fiber, if this is linear, um, then f is Frechét differentiable. Okay. Um, now, but this only works in finite dimensions. So only always true in finite dimensions. It may be false in infinite dimensions. It may be false in infinite dimensions. So in infinite dimensional spaces, the Gâteaux derivative is extremely weak compared to the Frechét derivative. But in finite dimensions, the playing field is sort of leveled out. Um, okay, so so we can talk a little more. Um, we note now that even though we talked about differentiability, so now whenever we talk about differentiability, I will mean the Frechét derivative, um, because we'll define what it means for a function to be smooth, and then everything from then on we'll just talk about smooth functions. So whenever we talk about differentiable from now on, we'll talk about smooth function. We'll talk about Frechét differentiable functions. Okay. If so, now consider let f be Frechét differentiable. Let f(x,y) be Frechét differentiable. Um, then we note that df. So if it's when I say it's Frechét differentiable, I mean it's Frechét differentiable at every point. So Frechét differentiable at every point in x. Then the derivative of f, or the Frechét derivative of f, is a function from x that goes into the space of linear maps from x into y. Okay. And the reason I make this small distinction is because um, this may not be continuous. Um, Linear maps may not be continuous in infinite dimension spaces. So we'll just restrict ourselves to linear maps. Um, but um, but the space of linear maps, well, the space of bounded linear maps is a Banach space. Okay. The space of bounded linear maps is a Banach space. So in case um, df, so in case df is a map from x into xy. So when I use this, I mean bounded linear maps x to y. So in case we have um we we may ask if df is differentiable. So we may ask if the derivative is differentiable. And the reason we can ask this, so I'll just make a side note here that the space of bounded linear maps is a Banach space. with the soup norm, right? So we can ask if this is differentiable. Um, so now we can already see that we can only ask if the map is differentiable if it's bounded. But in Banach spaces, bounded um, linear maps are equivalent to continuous linear maps. So so if df exists and is bounded, then df is automatically um, automatically continuous in A. Okay. So what I mean by this is the map A into df at A is continuous. Um, Now we note that okay, so there's a very slight um there's slight differences here. So when we say that df maps into the space of bounded linear maps, um, that's saying that the map df of A is bounded, hence continuous. So let me write this here. In other words, df of A from x to y is bounded for all A and x. Okay. But if df as a map into the space of linear maps is itself bounded, then it's already continuous. So there are slight distinctions between when we talk about boundedness of the derivative. And we have to be very careful when we're saying, because one condition is much stronger than the other. Okay. So we say that f from x to y is of class C1. So in other words, we'll write f in C1 x to y if df of A exists um, for all A, um, and df is continuous. Okay. So so being C1 is pretty nice because um, not only does the derivative exist and dfa is bounded, we also have that the derivative as a whole is bounded. Okay. Okay. So so let's continue now. Um, this means that we can now define the higher derivative. So um, now we define d squared or the second derivative of f at a point A. And now it'll take in 2 points. So x and give you a element in y. Um, and how do I explain this? Okay. So it has to take in two things because firstly, so it has to be like this, since df of A at a point H is so df of A is a map from X into Y. Um, so we can then look at the second derivative as you moving a little bit in this function space, and then another point on how does the value of the function then change. Okay. So it's defined this way, um, and is bilinear. Yeah. So what this means is that um, the second derivative at a can be thought of as a two zero tensor over x that takes values in y. Um, and let's sort of just write out the definition of this second derivative. So it's the limit as h goes to 0 of the norm of df of a plus h minus df of a minus d squared f of a. Um, so okay, there have to be two things, I guess. Hmm. No, this looks right. Yeah, so now this is now has to be so oops. So we can see that this has to be a map um on x to y. And then this is over the space of bounded linear maps over h and x, and this equals 0. So we see that it has to be bilinear. Um, and then similarly, we can define higher degree analogs. Uh, so then we define D3F at A to be a, a trilinear map that takes values in Y similarly. Um, Hence, we can define DNF at A to be a map that takes in n vectors in X and gives you values in Y. That satisfies the limit definition. We now say that F is smooth if all if smooth at A and X if D and F at A exists for all n in n. Okay. And from now on, we'll mostly look at only smooth functions. Um, so smooth functions are very nice, as we'll see. Um, and let's actually let's look at some examples of maps so that we get used to, taking the derivative of a function. So consider so examples. Let's do one example, and then once we do this example, we'll then talk about we'll then talk about like some very important theorems that hold from single variable calculus and some that actually extend. So not extend, some that are actually genuinely new for like higher dimensional spaces. So example, let's look at the function um, from R2 to R given by let this just be a linear function. Okay. So so let's look at this case. M to n is linear. Now, I hope you can see very immediately that the derivative of f must be f. So we check that. um, df at a equals f. Okay. So to do this, note that the limit as h goes to 0 of the norm of f of x, sorry, a plus h minus f of a minus df of a at h, okay, and rm over the norm of h and rn is nothing but the limit as h goes to 0 of, so using linearity, I can break this up. Um, this should be a minus h minus f, um, f of, oh wait, I have, this should be a plus here, this should be a minus, this should be f of h or m all over the norm of h and rn, but the top part is just 0, so this is 0. Okay. Um, so the derivative of a function, so a derivative of a linear function is just the linear function itself. Um, on the problem sheet, I've given where we, instead of linear functions, we look at multilinear functions. And we look at tensors, and we see that, okay, if we have a K0 tensor that takes values in some Banach space, then that must automatically be uh, Frechét differentiable or just differentiable. Okay. Now you might have heard of the partial derivative, and we can similarly define the partial derivative of a function um, over Banach spaces. So say we have x can be written as a direct sum of finitely many pieces. Okay, let's say it's m many pieces, and we have a function f from x into y. Now a point in x, a point a in x can be written as a equals a1 blah 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 up to am, right? So we can look at each component individually and then look at the derivative from that component into y. So so each for each I between 1 and m, we have a map. Um, I don't know how to exactly write this, so I'll call this fi a. Okay, and what that's supposed to mean is it's a map from xi into y given by um fi at a x is equal to f of a1 up to ai minus 1, and then I replace only the ith component with x, and everything else is the component of a. Now this is a function from a Banach space because xi is a Banach space into y, and then I can ask, is this function differentiable? Okay, so is this differentiable? Differentiable. And if it is, we say that this is the ith partial of f at a. Then we define d I f at a to equal d of f I a. Okay. So this might be a little confusing, so let me write it out like this. Okay. So the partial derivative is just I restrict all other component I restrict all other components, and then I define a map from one where I leave one component free, um, and then I write everything out. Um, in finite dimensions, this idea is very nice. In finite dimensions, this is nice since Rn is simply R direct sum with R n times, n times. Um, and so the matrix representation of df at A is simply the matrix of partial derivatives. So that's very nice, right? That's very nice. Um, Moreover, one can now check also. One can check that if df if f is C2 or above, um, check exists exists and is continuous, um, then d squared f um, of A is actually a symmetric two tensor, 2, 0 tensor. So if I remember, I think we wrote it like this. Um, so yeah, it's symmetric, which is very nice. Um, and then we'll actually make use of this symmetry in a lot of places. But it does require that we work with functions that are at least C2. Um, and that's why, again, we restrict ourselves to smooth functions. Yeah, we restrict ourselves to smooth functions, and then you know, we may or may not, um, we may or may not loosen the conditions later on when we talk about PDEs. Um, but for now, everything moving forward will be smooth. So let's do an example. If we look at the function f of x, y, given by x squared plus 1, sorry, x squared plus y squared plus 1, then f is smooth. Um, Moreover, df um, is given by 2x, 2y. Okay. And then d squared f is given by 2, 0, um, 0, 2, and so on. Um, okay, so that's very nice. So derivatives are nice. Partial derivatives are nice. Um, if you look at the problem sheet, there are yeah, if we look at the problem sheet, then you'll see that if you look at the problem sheet, there are many practice questions involving partials and just computing partials. Okay, now let's talk about the three main theorems that hold for Frechét derivatives. Three main theorems. I could be funny and call this the three hard theorems, but yeah. Um, okay, so the first one is chain rule. And so if I have a function f from x to y, that's differentiable at a and x, and I have another function g from y to z, differentiable is differentiable at f of a, then g compose f from x to z is differentiable at a. Okay. Moreover, the derivative is given by what we would expect. So dg at f of a composed with D F at A. Okay. So chain rule works nicely. The second one is the inverse function theorem. Inverse function theorem. Okay. And the inverse function theorem is defined as follows. So if f from x to y is C1 at A in X, okay, and df of A from X to Y is invertible, okay, um, then f is invertible in some neighborhood um, V of A, and moreover, f from, sorry, f inverse um, is differentiable um, at f of A with df inverse of A simply being df of A inverse. So okay, we now have to be slightly careful because V um, V may not be all of X. So it may not even be a vector space. So in this case, how do we define the derivative? We note that any open set, so note V may not be Banach. Um, but that's not too much of an issue, to be honest, because it's in the codomain space. So we can just inherit everything from X. Um, we can inherit everything from X. In terms of the norm, um, yeah, for in terms of the norm. Um, but it may not be Banach, but derivative is still defined. And this is because limits are local properties. Limits are local. And V is locally convex, right? By local convexity, I just mean at each point there's uh, you can actually show that every open ball is convex. And then since V is open, um, so I guess I should actually mention this. So this is open. Um, since it's open, each point has a ball around it, and each ball is convex. So if I take the limit to zero, um, the line segment along A must be at that point. So this is not too much of an issue. Um, so yeah, everything makes sense here, and we can also using the above, using the fact that open sets are locally convex, uh, we um, we can define um, derivatives for maps f from U into Y, where U is open in X, and the derivative is defined exactly the same. So df of A is still a linear map from X to Y. Because again, like close enough we can Like if H has small enough norm, then H is contained in some open ball centered at A, which is contained in U. So the limit eventually makes sense. Yeah, and then we can define C1 functions on U, C2 functions, and so on. Okay, so this is the inverse function theorem. And finally, we have the inverse implicit function theorem, which states that if f um, is C1, suppose also that f of x0, y0 is equal to 0, and df of x0, y0 at 0, y, I'll call this g of y, is an isomorphism from y into z, then there is a neighborhood. There's a neighborhood u of x0 and v of y0 and a Frechét differentiable function h from u into v such that f of x h y is equal to 0 and f of x y equals 0. Um, so you have my things backward here, I think. So Frechét differentiable, no, no, I had it right. Sorry. Um, this should be an x though. And if and only if y equals g of x. Um, this should be h, sorry. Okay. For all x, y in u cross v. Um, we're gonna actually use the we're gonna actually use the implicit and inverse function theorems a lot when we start talking about manifolds. And to get an example of why we might use this is the following. So f of x, y equals x squared plus y squared minus 1. Then f is f satisfies the conditions. F satisfies the conditions at each point x, y in S1, right? So there's an open neighborhood around each point in S1. Um, so for example, you can be this set -1 to 1, and V is the open set 0 to 1. Then h of x is defined as the square root of 1 minus x squared. Okay. Um, this is for x0, y0 equal to 0, 1. So we'll see that the implicit function theorem, it will be useful when we want to talk about um, how to define charts, how to define smooth charts for a subset of R. Um, and then we can use the implicit and inverse function theorems appropriately um, to get these charts. So we've pretty much already shown that S1 is a manifold. Um, Yeah, and so that is it for this. Um, and so yeah, whenever we talk about being differentiable now, we will strictly restrict ourselves to the case of Frechét differentiable. Um, Moreover, we'll also assume that all our functions are smooth, um, unless otherwise stated. Usually you can get away with being C2 or something, but at that point you might as well just be smooth. Um, so yeah, I will see you all next week. Bye bye.